So welcome you to this lecture. So in last module, we described a testing problem as a 2xn problem, as a 2xn decision problem. Now what I'll try to do today is I'll try to give a geometric interpretation of any 2xn decision problem, or in particular I'll be in a position to give geometric interpretation of a testing problem as a 2xn problem. Now advantage of visualizing a decision problem geometrically is you can answer a lot of questions which come to your mind. For example, whether Bayes rule is always minimax or not. Can I have a Bayes rule with a non-constant risk which is minimax or not? Whether all Bayes rules and all admissible rules are the same or not. So once we have a nice geometry, we can understand and answer such questions. So in today's lecture, I am going to see a geometric interpretation for testing or 2xn problem. So what I have is, I have a parametric space omega. Let me label those elements of the parametric space as 0 or 1. Now in the case of testing problem, my omega was the set of probability distributions which was available to us. So there was f0 and f1. So 0 is corresponding there to f0 and f1 is corresponding to f1. So I have a two unknown state of nature. I can always give some names to them. I'm giving them name as 0 and 1. For example, in the testing problem, 0 corresponds to f0 and 1 corresponds to f1. And corresponding to this, I have only two xn's available to us. So I have to guess what is the true state of nature, 0 or 1. I say my xn is 0 and 1. So 0 corresponds to saying that 0 is the true state of nature. Taking xn 1 means saying that, taking xn that 1 is the true state of nature. Let us look at decision rule the way we did in the testing problem. Delta, so decision rule, so let me write down decision rule is delta, or keep an x, and what is this? Is a probability distribution on xn space for every observed value of x. Right? So what I assume is my data is x. That is given to us. I know decision rule, I say that decision rule for every observed data point is a probability distribution, which is basically a randomized decision rule. So that means once you observe x, you don't immediately take the xn. You go for some kind of randomization which is equivalent to observing one random variable yx. And then whatever is the observed value of yx, that you take as an xn. Now if yx is a degenerate random variable, that corresponds to a situation where you are dealing with non-randomized decision rules. So that's a general definition of a delta dot given x. So note that for any decision rule delta naught, delta 0 given x corresponds to probability of taking xn 0 given x equal to x. Delta 1 given x is probability of taking xn 1 given x equal to x. So of course, since delta is a probability distribution on only 2 points, delta 1 given x has to be same as 1 minus delta 0 given x. So in fact, once I know delta 1x or delta 0x, the other quantity is automatically determined. So thus, we can take a decision rule delta to be mapped from where 1 minus delta x is same as delta of 0 given x, which is probability of taking xn a0 given x. And so delta x again is nothing but probability of taking xn 1 given x equal to x. Now the reason I am doing it is I don't want to carry all the time delta 0 given x and delta 1 given x. I just have a delta x, because here delta 1 given x is determined through delta 0 given x and vice versa. So as well I can represent one of them as delta x, and the second I know is 1 minus of that. So that is what exactly I have done. So 1 minus delta x for me is a probability of taking xn a0, and delta x is a probability of taking xn a1 given that data is observed as small x. So in other words, a decision rule delta is only a map from sample space x to 0 1 such that delta x denotes the probability of taking xn a1 given x equal to x, and 1 minus delta x denotes the probability of taking xn a0 given x equal to x. Let us consider the loss function as usual. So I have loss function LFA. Where f is f0 or f1 and a is same as a0 or a1, which is my let me not use f0 and f1 because now I have shifted to 0 1. So L theta 1, L theta a, where theta is belonging to omega, which is 0 1, a belonging to xn space, which is also 0 1. So what I have is, in certain sense, my loss function is defined in terms of only 4 quantities. And I normally take my loss function to be non-negative, and I say its value should be 0 whenever I am making a correct decision. So as we did in the case of testing, let us make it in the form of a matrix, a loss matrix. So my theta is 0 or 1, and let us say a again 0 to 1. Now these are L0 0. So that means loss when I take xn 0, and 0 is the true state of nature. So that means my decision is a correct decision. So there is no loss. I can take this to be 0. This is loss in taking xn 1 when 0 is the true state of nature. So that means my decision is not a correct decision. So there would be certain loss b over here. So let me take b to be positive. Similarly, L1 0, that means I am taking xn 0, though 1 is the true state of nature. So this, in this situation also my decision is not a correct decision. So there would be some positive loss. Let me call that as a C. Again this situation where I am taking xn 1 and 1 is the true state of nature. So that means my correct decision. I am making a correct decision. So here also loss is 0. So now if this is the loss function, let me talk about what is the risk. Now note that to evaluate the risk, which is nothing but average loss, and if I have to calculate average loss, I have to keep in mind that randomization has taken place at 2 stages. Stage number 1, using the decision rule delta for a given observation, and then I take the average over all possible values of the data I can get. So the first stage average of loss is L star theta delta x. What is this? This is nothing but average with respect to yx of L theta yx. Now this 1 minus delta x is what? It is a probability of taking x and 0. So this is same as probability that yx is equal to 0. And what is the delta x? Delta x, probability of taking x and 1 given x when x is observed. So this is same as probability yx is equal to 1. So once I am taking average with respect to yx, I see what are the possible values yx can take for given x. So yx can take value 0, which is same as whose probability is 1 minus delta x, and L theta 0. Then yx can take value 1, whose probability is delta x, so delta x into L theta 1. So this is the average loss. Now I consider the risk function R delta theta. What would be the R delta theta? This would be same as expected value under theta of L star theta delta x. So I can talk about theta at 2 points. Theta so for any decision rule delta, risk function consists of only 2 points, R delta 0 and R delta 1. So I can talk about V delta as, for any decision rule delta, as R delta 0 and R delta 1. So for any decision rule delta, rather than calling it as a risk function, I call it as a risk vector, because there are only 2 components of risk of delta. One is R delta 0 and one is R delta 1. So I call this as risk vector of decision rule delta, which is belonging to script A. So what I see is for any decision rule delta, when I talk about a risk, I can talk about a point in R2. So this is a point in 2-dimensional Euclidean space R2. So the risk set is a point in 2-dimensional Euclidean space. Now as I vary delta, I get a collection of values of V delta. Now that collection let me call as a risk set. So let us say D is the class of all decision rules. Then the set S, which is collection of all those V delta, says that delta is in D. I call this set as a risk set. Now note that V delta from here is a point in R2, 2-dimensional Euclidean space. So this is a point in 2-dimensional Euclidean space. This is varied as delta varies over D. So this would be a subset of R2. So a risk set is always a subset of R2. And this would have certain geometry. So one thing which I can immediately say is risk set is always a convex set. So let me do the theorem. S, which is a risk set. So for any decision problem, the risk set S is a convex set. So how do you prove this? That means you look at 2 points in the risk set. So let me call those as V delta 1 and V delta 2. So let V delta 1, so that means there is a decision rule delta 1, R delta 1 0, R delta 1 1, And there is another point in this set delta 2, which is r delta 2 0, r delta 2 1 belong to the risk set S. What I have to show is any convex combination of them also belongs to the risk set S. So what I have to show is beta times v delta 1 plus 1 minus beta times v delta 2 belongs to risk set S. So my claim is beta delta 1, sorry, beta v delta 1 so I have to show that beta delta v delta 1 plus 1 minus v delta 2 is a point in S, or in other words, it is a risk of some decision rule delta. So what should be a natural contender for which this would be a risk set? The natural contender would be beta times delta 1 plus 1 minus beta times delta 2. So if I can show that the risk of beta delta 1 plus 1 minus beta delta 2 is same as this, that means it is a risk of some decision rule. But for that, first I have to show that beta delta 1 plus 1 minus beta delta 2 is a decision rule. That is the first step I will do. Once I have established that it is a decision rule, I will try to see what its risk is, and then I will show that its risk is same as this. And from where I will conclude that this is a risk of some decision rule. So note that beta delta 1 plus 1 minus beta delta 2 is a decision rule. Now to show that it is a decision rule, what do you have to show? You have to show that for every x, it only takes value 0 and 1, between 0 and 1. For every x, delta 1x is between 0 and 1. For every x, delta 2x is between 0 and 1. So beta times delta 1 plus 1 minus beta delta 2 would also be between 0 and 1. And what is the decision rule? It says you reject h naught, sorry, you take xn a1 with probability beta delta 1 plus 1 minus beta delta 2 and take xn a0 with probability 1 minus of beta delta 1x plus 1 minus beta delta 2x. So that is a decision rule. So this is certainly a decision rule. Now the only thing I need to say is what is its risk. So let me call this as delta star or delta 3. So what I see is what is L star theta delta 3 x. What is L delta 3 star x? It is 1 minus, it is average of L theta e. So this is same as average with respect to the probability distribution of delta 3 of L theta e. So delta 3x. Delta 3x can be treated as a probability distribution. It has a two component, delta 3x and 1 minus delta 3x. Delta 3x as it is a probability of taking xn a1. So this is delta 3x or L theta a0. A0 is 0 because taking xn 0 and it takes xn 0 with probability 1 minus delta 3x plus taking xn a1 which it takes value with delta 3 L theta 1. So what does that become? So this is same as 1 minus delta 3x is same as beta times 1 minus beta times delta 1x minus 1 minus beta times delta 2x times L theta 0 plus delta 3x which is same as beta times delta 1x plus 1 minus beta times delta 2x into L theta 1. So what I do is I can write down this as, I make this as beta times 1 minus delta x. So that means I'll have to, 1 minus beta plus beta times 1 minus delta 1x. All right, because all these I want to write down as 1 minus because of this. So this same as beta times 1 minus delta 1x, and then 1 minus beta goes over there, so it becomes 1 minus beta delta 1x plus 1 minus beta 1 minus delta 2x, right? Cut. L theta 0. I've just written down the first term over here, everything in terms of 1 minus delta 1x. Oh, sorry. Everything is in terms of 1 minus delta 1x. So this is same as. So let me just erase it so that. So this becomes beta times 1 minus delta 1x plus 1 minus beta times 1 minus delta 2x. All right. L theta 0 plus this I remain as it is, because this with L theta 0 I know that 1 minus delta comes, and that is the reason why I wanted to convert it delta 1 into 1 minus delta 1 and delta 2 into 1 minus delta 2. Once I do that, I see this can be written as this quantity, so which is same as plus beta times delta 1x plus 1 minus beta times delta 2x into L theta 1. And what does that become? This becomes beta times, I just see the term of beta, 1 minus delta 1x L theta 0 plus delta 1x times L theta 1. So that is as if you are talking about average of loss using decision rule delta 1. So that is same as L star theta delta 1x plus, what is this quantity? 1 minus beta becomes common, 1 minus delta 2x L theta 0, delta 2x into L theta 1, which is again as if you are taking the average of loss L theta a using the decision rule delta 2. So this same as 1 minus beta L star theta delta 2 x. So what is R delta theta, R delta 3 theta, which is same as expected value and the theta of L star theta delta 3 x. And this turns out to be, from here, beta is a constant, so beta times expected value of L star theta delta 1x, which is nothing but the risk of decision rule delta 1. So B times R delta 1 theta plus 1 minus beta times R delta 2 theta. Right? So what does this say? That the quantity beta times R delta 1 theta plus 1 minus beta R delta 2 theta is nothing but risk of a decision rule delta 3. Or in other words, this is a risk of some decision rule. This is a risk of some decision rule, that means it belongs to a risk set. And that is what I had to show, that beta times v delta 1 plus 1 minus b delta 2 belongs to a risk set. So this shows that risk set is always a convex set. Now if it is a convex set, now I can try to look at how does a Bayes rule would look like. So now one can show the converse part also. Given any convex set in R2, I can find a decision problem for which this convex set is a risk set. Given any convex set S, one can construct a decision problem for which S is a risk set. So what I know is, if I look at any point in xy plane, so I can denote it by x-axis by r delta 0 and y-axis by r delta 1. Now as you vary delta, you get different points over here. So if I look at any convex set over here, let us say a set of this kind, this is a convex set. Any 2 points, if you look at the line segment joining them, is inside the set. So this can be considered as a risk set. Now note that here every point over here corresponds to risk of a decision rule. So in a certain sense, every point over here corresponds to a decision rule. There is a possibility that more than one decision rule may correspond to the same point, because there is a possibility that more than one decision rules may have the same risk. But the fact is, each point over here corresponds to at least one decision rule. So if I see the geometry of this, I can get a lot of information about various questions concerning decision rules. So let's try to see first the Bayes rule. Now for every Bayes rule, I need to have a prior distribution. Now here omega is only 0 or 1. So my prior distribution would be a discrete probability distribution whose support is only 0 or 1. So let me call this pi of 0 as p and pi of 1 as 1 minus p. So Bayes risk of any estimator delta would be how much? It would be the risk, the classical risk, take its average. Classical risk has only 2 points, r delta 0 and r delta 1. So it would be nothing but p times r delta 0 plus, because theta is equal to 0, probability is p, 1 minus p times r delta 1. So now suppose I have to find a Bayes rule. So I have to find a Bayes rule, find a decision rule delta such that this quantity is minimum. That is a Bayes rule. So let's try to see. Now let us try to see if this quantity, if this is r delta 0, this is r delta 1, and suppose my risk set is like this. The extreme points is you might have r delta 0 as 0 and 1. So 2 extreme points would be this So what could be two extreme points? One can calculate from that loss function. So one thing is, one always take delta to be, one gives whole weight to delta 0. So extreme points would be, this would be B, this would be C. One can easily see that. So that means this would be B0 point, and this would be 0C point. As you vary delta, these points would always be there. You can see that B corresponds to certain risk. You can see where does B belongs to. So B and that you can immediately see. Let me just leave that as an exercise. Now let us look at this quantity. This quantity would be some quantity C. So let us look at in whole R2, this line is, let us say Px plus 1 minus Py is equal to C. Now note that my P is fixed. My prior P is fixed. So what is happening? If I look at this line, the slope of this line is fixed. Only these points are changing, and these points are changing according to the decision rule. But the slope of all the points would be the same. So I'm trying to look at a point x and y in over here, which touches this as I vary C. So I keep on varying C. There is a possibility that it might touch this at a point. Not a very nice figure, but it touches this at a point. So this would be a risk of a Bayes rule, right? Because Px plus 1 minus Py is equal to C. As x and y are varying, this line is varying, except that the slope of the line remains the same. The intercept changes because points x and y are changing. But I have to find x and y which is there in the risk set, because that would be the risk of a decision rule. So what I do is, that means I keep on changing its intercept, so I'll get a series of parallel lines, and then I see where, for what intercept that line touches this risk set S. Now this point would correspond to Bayes rule with respect to P, because P determines the slope. P is fixed, so slope is fixed. So I can find the Bayes rule. Note that this is not a Bayes rule, because these are risk of a Bayes rule. So any estimator whose risk is same as this would be the Bayes rule. So you can get the Bayes rule over here. Now you can, as I said, you can answer a lot of questions over here. What would be the class of admissible rules over here? Let us look at, again, the same kind of figure. My risk set is this. This is R delta 0, R delta 1. This is my risk set. Admissible rule is which cannot be improved. So note that for all the points over here, so you cannot get any estimator. So it would be, what would be the points corresponding to inadmissibility estimator? All those points S and T, such that there exists a point such that S is less than or equal to S naught and T is less than or equal to T naught for some S naught and T naught, and with strict inequality for some S naught and T naught. Note that any point which is over here, any point over here which is above the lower boundary, for this, if I compare this with this point, for this point, x-axis is same and y-axis is strictly smaller. So this point becomes inadmissible. So any point which are not there in the lower boundary and above the lower boundary would be inadmissible. What about the points in the lower boundary? If I look at point over here, can I find an estimator such that this holds with strict inequality? Can I find S naught and T naught such that this holds? for this point ST? The answer is no, because the moment I move, all our above points cannot be. Only it could be the lower point. If I move over here, what is happening is, although x-axis is decreasing, y-axis is increasing. So they are not comparable. So all the estimators in the lower boundaries are not comparable. So they are the only admissible estimators. So lower boundary corresponds to admissible estimators. Now note that in this case, depending on the slope of this line, any point in the lower boundary can be touched by lines through some slope. So it looks like they also, all these points corresponds to the Bayes rules also. So in this case, it looks like the Bayes rules and admissible rules are the same. So now the question arises, are the Bayes rules same as the admissible rule? The class of all Bayes rules is same as class of admissible rules. So the question is, class of all Bayes rules is the same as class of all admissible rules. Certainly that will not be the case. One can always consider the extremes. Let us look at this situation. Now in this case, all these points can correspond to the Bayes rules. They would correspond to Bayes rules in the sense that R delta 1 is minimum for them. So that means for the prior which gives whole weight to 1. So that means I consider pi 0 as 0, pi 1 as 1. So R delta pi in that case turns out to be only R delta 1. So the Bayes rule would be for which R delta 1 is minimum. So all these corresponds to the Bayes rule. And what is the admissible rule? Note that any point which is not in the edge, it is on this side. For that point, I can consider the edge whose x-axis is same as that point. So that means risk at 0 is same as that. Sorry, I consider any point over here for which risk at delta 0 is smaller for the edge. So risk at delta 0 would be smaller, and risk at theta is equal to 1 would be the same. So all these points would be inadmissible except the edge. All points except edge correspond to inadmissible rules. And they are Bayes rules also. Why? Because Bayes rule is the one for which R delta 1 is minimum. R delta 1 is minimum for all these rules because R delta 1 is same for all these rules. Inadmissible Bayes rules. So the class of Bayes rules may not be same as the class of admissible rules. Let us try to see how does a minimax rule looks like. Let us look at this point. My supposed risk function is again the same, R delta 0, R delta 1. Note that this is a risk set because it is a convex set, square is a convex set. So if I have to look at the minimax estimator or minimax rule, the one for which supremum is maximum. So what I do is I draw the line r delta 0 is equal to r delta 1. So it looks like this should be a minimax rule. Because if I look at any point over here, the supremum is going to be how much if I look at over here? For this point, supremum r delta 0 is same as r delta 1. If I look at any point over here, what is its supremum? Its supremum is the x-axis over here, which is bigger than the supremum of this. So all other points will be corresponding to the non-minimax points. So the minimax rule would be only this, which corresponds to intersecting r delta 0 is equal to r delta 1 with the risk set S. You can answer a lot of questions. I'll just give an example. Can you have a minimax rule unique? Now this tells you Bayes rule may not be unique, minimax rule may not be unique, because you can always take, suppose this is x equal to y line, r delta 0 is equal to r delta 1, and r delta 0 is over here, r delta 1 is over here. Suppose your whole risk is on one side. This is a risk set. So for any decision rule delta, what would be the maximum risk? Maximum risk will always be greater, this is the reason x greater than or equal to y. So the maximum risk will always be r delta 0, because this is x equal to y line, and if this is the risk set is lying just over here, then maximum risk is the x-axis, which is r delta 0. Minimax rule would be one for which r delta 0, that means, is minimum. And r delta 0 is minimum for all of these rules. It is the same. So minimax rules. So this corresponds to a situation where minimax rule may not be unique. This also corresponds to a situation because we have seen in a lot of applications, minimax rule has a constant risk. Constant risk means r delta 0 is same as r delta 1. Here all these rules are minimax, but r delta 0 is not same as r delta 1. So a minimax rule need not have a constant risk. So they are also same as non-unique. And this also gives you an example where you say that minimax rules having non-constant because here saying that a decision rule has a constant risk function, that means r delta 0 is same as r delta 1. That means it does not depend on theta. R delta theta is same. That means r delta 0 is same as r delta 1. But in this case, what we have seen is minimax rules is over here. And in fact, here r delta 0 is strictly bigger than r delta 1. So this illustrates situation where you have a minimax rule and they do not have a constant risk. So the purpose of doing this was you can answer a lot of questions which come to your mind. We answered few of them. That whether the class of all admissible rules is same as the class of all Bayes rules, the answer is no. We could see it geometrically. Is the minimax rule unique always? No. Would the minimax rule always have a constant risk? The answer is no. So that's all about the geometric interpretation. So let me stop over here, and then we'll meet in the next lecture, and where we'll take up the next topic in parametric statistical inference. Thank you very much.